Welcome to State of Simulation, the podcast all about multiphysics simulation, where we stay up to date with what's working, what's not, and what needs to change. Each episode features an open conversation with the engineers and technical leaders shaping the future of physical product development. I'm your host, Jukka Knutinen, and in today's episode, we're speaking with Chris Chaggares, President of RIA and the Head of Research and Development at Sonell. Chris is a seasoned ultrasound transducer designer, simulation enthusiast, and longtime innovator in the field of medical imaging technology. We'll talk about how Chris uses simulation in his work, where he explains how simulation helps him test ideas, understand how things work, and make decisions faster. Chris shares his approach, the challenges he faces, and what he hopes simulation will look like in the future. Without further ado, let's get started. I guess we could just kick off by introducing yourself. So who are you and what do you do?
All right. My name is Chris Chaggares. I'm I guess I'm a equal parts ultrasound transducer enthusiast, designer, and inventor. I've been fortunate to spend several decades and some change designing ultrasound equipment and primarily transducers. I got started with a real intention to become some kind of a laser jock. I really loved lasers and still kind of do. And so to that end, I started out in electrical engineering and somehow along the way stumbled into ultrasound and these marvelous devices that can produce ultrasound from electricity. And that steered me into a different direction. And I ended up pursuing a mechanical engineering degree in graduate school after electrical, and stumbling into the medical physics department and getting my hands dirty in materials science, and ultimately joining a company called Visual Sonics, where I was fortunate to be part of an exciting journey there and develop a lot of ultrasound transducers, and along the way discovered finite element analysis and simulation in these multiphysics problems that are so interesting to me for the rest of my career and right up until today.
Awesome. So sort of very concretely speaking, what kind of problems are you solving, like in your day-to-day job?
Fantastic. Well, again, I've been fortunate to be able to spend most of my career developing and researching brand new technologies related to ultrasound transducers, and that's where I enjoy and find my passion. I think well married to my effort, and so I have been generally developing brand new technologies to solve ultrasound transduction problems, and that's what I still do today by developing transducers for customer specific applications and requirements. And with simulation, I found over the years and very much so today, a tool that I can use from inception to completion of a product. And it's something that's instrumental in interacting with customers, with my team, with our test group, and even in production to help understand problems. And so I think that using simulation in order to gain intuition and understanding about what you're creating is a tremendously valuable part of working in a field that is so complex and so poorly defined in terms of boundary conditions and coupled physics problems that we see in ultrasound transducers.
That's interesting. I've heard you compare the utilizing these simulation platforms to a video game of sorts. You mentioned Minecraft specifically.
That's right. It's my ultrasound Minecraft world that I can go in and play inside and see how things work at a level that's just not attainable in the real world. You know, I'll often make a transducer that has elements that are microscopic or has components inside that have properties, and I know intuitively as an engineer and someone who's studied this field, I know they're moving and they're vibrating and they're doing certain things, but there are so many aspects of how they're interacting with each other and with the outside world that I simply can't visualize. There's no available forum for me to gain intuition into how a pillar of an array that is microns tall is going to interact and vibrate and move when things get really complicated. And so I really try to extract as much information as I can from the simulation process early on, and then I always speak of the investment. So like any good video gamer, you have to put your hours in order to get good at it. And so I really believe that a lot of the value of simulation is doing your homework on the materials front, on the characterization side, doing everything that you can with the intuition that you have at your fingertips and your eyes and the other senses that we have, and sitting at your microscope, et cetera. Measuring and characterizing your materials really well, and then you can dive into this virtual space. And I believe one of the great values of simulating ultrasound transducers is the ability to rapidly iterate and experiment in a space where you have confidence in the outcome. So if you put in the effort to understand your materials and to verify the very small blocks along the way, the more powerful the tool you have, of course, the better. But ultimately, even the best simulation software is going to fall short if you haven't understood the inputs that you're going to use in that software. But once you do and you gain that confidence, suddenly you can experiment on a scale of hours and days where it would be weeks and months in the real world. And the cost, of course, is going to be a fraction. And so for me, yeah, it's always been about building up intuition and trust in my simulation space. As I understand my materials and the simulated results better, I can put them together in more and more ambitious and complicated ways and begin to trust the outputs from that simulation.
Sounds like you're sort of very lucky, and I don't know, you can say if that's a unique position, but at least you sound very fortunate to be in the position where you can really test a lot of things and get the results fast. So
Absolutely.
Do you simplify them, or do you just have the computing power at hand to be able to perform those kind of studies?
That's a great question.
This podcast is brought to you by QuantScience. If you're like Chris and are using simulation to navigate complex multiphysics problems such as balancing material properties, dealing with meshing challenges, and long run times, QuantScience also might be exactly what you need. It's a cloud-native simulation platform built for fast iteration, large-scale 3D models, and tightly coupled multiphysics simulations. Whether you're testing new ideas, fixing design flaws, or optimizing for performance, also gives you the speed and scalability to explore freely without waiting overnight for results. To see how it works and request a trial, visit quantscience.com. Again, to see how it works and request a trial, visit quantscience.com.
It's always a balancing act. How much complexity do you build into your model? How much do you attempt to simplify in order to reduce compute time and cost? I think there's probably not a very easy answer to find the balance. But what I will say is I always try to test the validity of any kind of an outcome that I get from my FEA. Have I simplified it? If I have, how much should I really extract from the results? I will say for sure that there come points where you have to bite the bullet and swallow some compute cost and do a comprehensive model without too many simplifications. I'll share a good example. I've worked on piezo composites for many years, and I spent a long time trying to find an axisymmetric equivalent for a 1,3 piezo composite, and I don't know that one will ever exist. There are so many interesting interactions that occur in a 1,3 composite that are not axisymmetric, that every simplification, every approximation that I tried fell short. And even when I could get the electrical impedance to look right, I would lose some kind of lateral response within a material or something like that. And so I think one of the things you have to do is be brutally honest about what is the limitation to the results that you see in your simulation in terms of applying them to the next step. You can get very far afield if you misapply a result, assuming something that isn't valid, and moving on to the next step. So the other thing that I do is I use my lab as a touchstone frequently. So if I'm developing a composite, I'm going to run back to an impedance analyzer and verify the results of just that composite layer. And make sure that when I simulate it, that part works before I add it into a 12-layer transducer with a lens and a backing and an impedance matching circuit. And so I think it's important to not to overreach before you spend all of that compute time.
Makes sense. Now, well, again, it still sounds like you are currently very sort of well served with your tools and your resources at hand. What would sort of be the I'm sure that the situation is still not what you would see in your dreams. So what is lacking?
So maybe like Minecraft, I wish I could make something a little rounder than the blocks allow. There are limitations in terms of, sorry to stretch an analogy to the bitter end. There are limitations in terms of compute time, complexity. I think probably the largest one is the ability to rapidly iterate through the ideation phase without stumbling over too many assumptions. So I can't stress enough how often I have to go back and verify something. But on the other hand, sometimes the next step, when you go to that next complicated step, it can be an order of magnitude in complexity. So suddenly you go from 10-minute iterations where you're, okay, this is looking better. Oh, I should make this thinner. I should make this thicker. And then suddenly your next model is going to take 16 hours to run instead of 15 minutes. And so those are definitely a big aspect of challenge. The other side of it is there are still some large unsolved problems in terms of what you can realistically get out of a simulation. We're pretty good today at pushing ultrasound out into water, for example, from a transducer, right from electricity coming into a coax through some impedance matching network into a transducer, and out comes an acoustic field. But to move that acoustic field many wavelengths in that water, a lot of times we're going to take that output from the FEA result and we're going to move that into some kind of an analytical extrapolation regime and move that forward. And then things get even more questionable when you want to reflect off of a target and bring it back to a transducer. So ironically, in the laboratory world, the first thing almost every ultrasound transducer guy does is grab a reflector and fire a transducer in a pulse echo mode and look at how that transducer behaves bouncing off the simple reflector. To do that in the simulation world is harder than it sounds. In addition, the ability to take a large model laterally and understand its implications while also modeling the acoustic field any significant distance. Those problems, as soon as they become non-axisymmetric, as soon as they're truly 3D, they scale at the cube of the mesh. The other problem is we have so many amazing materials coming to fruition in the world today with the advent of AI-fueled metamaterial development and new alloys that are being created. There are so many opportunities for us multiphysics types that are concocting these amazing little alchemical devices that make ultrasound out of electricity and vice versa to put together, that trying to get those accurately captured into a finite element model and then meshed appropriately to get a real result is really a daunting challenge. And I think probably, maybe I mentioned before, but the number one mistake that I see with colleagues and friends as I chat about these sorts of things is they go a little light occasionally on that homework at the beginning of understanding the materials. Do you really know the shear velocities and the shear losses in a material that you're building an array out of, or did you just measure the speed of sound and the density and assume it's probably Poisson's ratio is probably 33% and we're good to go? So depending on how much you do or don't know about your materials, there can be limitations there. But I would say that leads me around to make the simple answer is the cost of compute, the cost of meshing your model accurately is a huge limitation. So I have a model right now that I'm working on, for example, for a really exciting new technology. I can't talk all about what that is right now, but I can tell you when there's one layer or one element in your design that's considerably smaller than everything else around it, that can be a tremendous limitation in your ability to accurately use your FEA. And that can require a whole bunch of jumping out of that wonderful virtual space where you can iterate rapidly and you can ideate and you can innovate, to I've got to go back to the bench, I've got to make something, it's going to take me a week, I've got to go and do a whole bunch of measurements, and then I got to go back in and see if I can verify that component, so I'm not wasting my time with all the subsequent iterations and compute time. So I would say the speed that we can compute complicated models is a huge limitation currently. I would, especially in 3D, where we're becoming more and more complicated, we rarely rely on a simple disk that's axisymmetric and has nothing going on. A lot of times things are composites that are not axisymmetric. Things have very complicated shapes and geometries. And so that's one. The other one is the ability to mesh these complicated geometries in a way that doesn't take hours and hours of writing code and hand making elements, and then also rapidly understanding and gaining intuition for our models. So maybe on the philosophy of how I simulate and why I've been able to find a lot of success from this is I really do believe, and that's why I use the video game analogy, that this is about gaining intuition in something that we don't normally have an opportunity to gain intuition in. And I have spent countless hours watching the outcome of my model in real time, and I'll often kill a build way before I get anything to post-process because it looks funny. And I'll change something, or I'll slow it down, and I'll stare at a movie over and over again, watching pillars vibrate and trying to understand how that's going to influence the device. And in order to do that, I need a fast, fluid simulation program that allows me to see those results in a meaningful amount of time. If I just have to hit the button and go to bed and look tomorrow, I'm going to find out the end result, but I may have no idea why I got the end result. And if I don't have a means to go back and interrogate my own model in a way that's accessible to my understanding, then I think I miss out on a lot.
Very, very interesting. I hear that, and it's kind of easy to assume that simulation is used a lot in exactly the first phases, like ideation and testing, etc. Is there any other stages sort of in the product development cycle where you use these simulations and the results?
Yeah, absolutely. So the other thing that I rely on a lot is the validation of a design to my model. As I build up a family of technology within our company, I'm going to do an awful lot of metrology with finished designs, and I'm going to go back and refine my model over and over again until I really can trust multiple aspects of it. Can I predict the acoustic pressures, but also the temperatures, and also the beam shapes and secondary effects? And then when I have that understanding, I have a really powerful tool to sell that to potential clients as we go forward. So when I have a client come in and they say, "Oof, I've got this problem," I have almost everybody either already has a transducer or a pretty good notion of why they can't get one. And so when they meet with me, I'm often able to take a preliminary stab through my simulation that if I've already evolved it to that level of confidence, where I can design a very first order approximation of what that customer wants. But then instead of telling them, I'm going to give you an F number this and a pressure that, and I'm going to try to reduce your side lobes or whatever it might be, I can show them a quick finite element model of the acoustic field that's causing them a problem and our proposed solution. And I can put that in pretty colors on a slide and make that really accessible to someone who's maybe a biologist or a doctor or somebody who knows they need ultrasound, but they're not entrenched in the field and the physics. And so it becomes very difficult for them to visualize, why are we doing or proposing what we're proposing? But when you can show somebody, here's the physiology you wish to interact with, and here's your acoustic field interacting with that physiology in the way that you asked for, that can be really, really powerful. It also gives us tremendous ability to predict success on a time frame and within a bound that helps them make their business decisions. So yeah, as a selling tool, I think it's tremendously powerful. It's also great when I'm talking to my partners and we're budgeting for a project, and I can say, well, guys, I made it already. Here it is. All we have to do now is make it in the real world because it already exists in the space within the technology we understand. And if I can't do that, they also know, hey, Chris, you're going to have to go back and sharpen your pencil for a while here. And it really helps us to keep ourselves honest about what we know how to do and what we don't know. The final thing I think I'll say on that front is IP creation. In a field like this where we're innovating, I've been fortunate and excited along the way to be able to file lots of exciting patents and create IP over my career. And one of the great things about FEA for me is it's a real sanity check. So when you think you've got a great new idea, if you absolutely can't make it happen under any attempt on your FEA platform, you either need a better FEA platform or you need to go back to the drawing board and understand why you can't. So for me, it's, again, I often describe it as a virtual laboratory. It's a place where I can go and try things out and test things out and sanity check them.
Makes sense. Yeah. Awesome stuff. Awesome stuff. Now, I suppose the sort of last question I have for you, the last sort of picture I wanted to paint is the future. So where do you see the entire field of multiphysics simulation? We can keep it in the ultrasound transducer context, or you can broaden it if you will. Where do you see it going in the let's say next 5 years?
Yeah. Okay. So I think one of the travesties is when I spend my day fighting with code, trying to implement something that I can absolutely simply envision or draw on a piece of paper, and it takes me 6 hours to get into a model. I think it would be spectacular to see that phase of model development become more intuitive, and to become a lot less reliant on some kind of syntax-based code. Even the CAD models that come in, I've often shied away because I'm like, I don't know what kind of mesh that's going to give me. Am I going to have to go and redo it anyway? And then it's code I didn't write. I think that the potential to get a really effective way to intuitively enter a model through some kind of a CAD process and then get a really robust mesh, a really solid introductory run of that model early would be huge. So if I could take my sketch, quickly get it into some kind of a three-dimensional modeling platform, and then hit run really early on and watch what starts to happen, and let my design creativity phase happen with the benefit of that intuition feeding feedback from the FEA model happen early before I've invested hours and hours in some kind of a model and code. And then I think the other thing I would say is an even more robust, I would love to see, there's always going to be a challenge between people's work and IP and widely available information, but I think there's a tremendous potential, especially in academia, to start building up a better database and understanding of materials. And then also for professionals working behind the quite worthy screen of IP and technology that they create, just a better way of entering and validating material information within the database, so that you're not constantly having to guess and try to understand. So I find that, for example, with piezoelectric materials in an ultrasound transducer, I think a lot of people have a very generic model of PZT that they stuff in their model, and then they wonder why things don't come out the right way at the end. And so I think an easier way to interrogate and enter good data for materials would be a second wish list. And then I think the third one would be the ability to rapidly compute large, complicated 3D models, even if it's with some caveats. I think one of the biggest problems is you hit go on a big, complicated model after you've done all your homework and you've got all your materials, and it's hours before you find out there was a syntax error, you meshed it wrong, and that can be quite difficult for people to cope with when they're on a budget and a deadline. And sometimes I think maybe people say, this FEA stuff, it's too slow, it's too clunky, and they just go back to their lab when maybe they're sitting on a gold mine and a potential. So I try really, really hard when I'm using what I have now to resist that big, complicated, all-inclusive model until I have great confidence that it's going to yield results. But it would be wonderful if I could hit that button and start to see results in a short time frame, and have the opportunity to stop it and interact with the model and tweak it until I see that the big spend in time to get to a final result is going to yield something useful.
Makes a lot of sense. Well, Chris, this was very insightful, and we're very happy to have you on. Thank you so much for taking the time.
Thanks, Jukka. I really appreciate it.
Thank you for listening to this episode of The State of Simulation. To stay updated with the latest episodes, webinars, blogs, white papers, and more, join our community of more than 6,000 engineers and engineer-minded people on our LinkedIn page, Quantscience. Thank you again, and see you in the next one.